Bismillahirrahmanirrahim. Assalamu alaikum. Dear students, welcome to chapter 6, class of CS131, discrete structures. And today we'll be talking about section 6.1, which is basically the basics of counting. In the last lecture, I talked about basic introduction to chapter 6, and this is how counting or why counting is important. This gives you a very basic idea of counting. You probably have studied this in your earlier classes, but this gets you into the let's say groove to understand the topic well. In the introduction, we first start off with an example which says that suppose that a password on a computer system consists of 6, 7, or 8 digits. Each of these characters must be a digit or a letter of the alphabet. Each password must contain at least one digit. How many such passwords are there? So notice that in this particular example, we are supposed to count or get a number of the number of passwords that exist with certain restrictions. The restrictions are that the password can consist of 6 characters or 7 characters or 8 characters, where a character is defined by it can either basically be a digit 0 to 9, that is it has 10 different options, or it can be a letter, that is it can be from A to Z. And here we are supposedly not going to differentiate between capital letters and small letters. If you take that assumption, then there are 26 letters, 10 digits. If you assume that the letter is differentiated between capital letters and small letters, then of course there are 52 different options, and 52 options plus options for 10 options for digits. So 52 plus 10, 62 different options. Each password must contain at least one digit. So that's another limitation that you need to be looking at. Although you have defined that the password, each letter, each character can be either a digit or letter, maybe 52 letters or one of 52 letters or one of 26 letters, as you may define. But the password must contain at least one digit, and that one digit is basically, you need to counter that somehow. So these kind of problems and the techniques that are needed to answer this particular question and a wide variety of similar other counting problems will be introduced in this particular section. And that's why you need to go through this section, and you'll be studying some rules and techniques to answer similar questions. Counting problems arise throughout mathematics and computer science. So this is one of the fundamental problems of mathematics and computer science, which arose actually for many long years, and which we have seen for a long time now. For example, we must count the successful outcomes of experiments and all the possible outcomes of these experiments to determine probabilities of discrete events. We must be able to determine the outcomes of experiments and all the possible outcomes of these experiments, etc. And these are typically used to calculate the probabilities of discrete events. So what is the probability that a certain event can occur? Well, the more options you have, lesser the probability of that particular event to occur. But of course, the more the lesser number of options you have, the higher the probability of a particular event to occur out of the given number of events. So to do certain kind of probability calculations, we just need to count the number of operations used by an algorithm to study its time complexity, for example. Although we have not discussed time complexity yet, but this is a topic that I intend to discuss at the by the end of this particular course. Suppose that a procedure can be broken down. Okay, so let's talk about the basic counting principles now. And the first simple principle that I'm going to talk about is the product rule. In the product rule, let us suppose that a procedure can be broken down into a sequence of n tasks. So a particular procedure can be performed in n different tasks, in n different ways, or n different, or order of sequence of tasks. So if there are n1 ways to do the first task, so for the first task there are n1 ways, and for each of these ways of doing the first task there are n2 ways to do the second task. So if you have to do it in two sub-steps or sub-tasks, and there are, for the first subtask, there are n1 different ways, and for each of these n1 different ways, you basically have got n1, you have got n2 different ways to do the second task. Then there are a total of n1 multiplied by n2 ways to do the whole procedure. So that's a simple product rule. And to understand it, let's look at a simple example. A new company with just 2 employees, Sanchez and Patel, rent a floor of a building with 12 offices. So there are 12 offices on the floor, and there are 2 employees who are sitting there. So how many ways are there to assign different offices to these 2 employees? So how many different ways are there to assign different offices to these 2 employees? Well, one notices that if you think about it, if I have to assign an office to Sanchez, I've got 12 different options, right? Sanchez can actually choose any one of the 12 offices. And for whichever one office he chooses, Patel actually has got 11 different options to choose offices from. So Sanchez has just got 12 options, Patel has got 11 options. And if that is true, then in total you have got 12 multiplied by 11 different options, different ways that you can basically assign offices. For example, Sanchez chooses office 1, then Patel can choose either of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That means that you can actually combine for Sanchez, if he chooses option 1, you can combine it with any of the other 11 offices. So there are 11 options for Patel. For if Sanchez chooses office 2, then Patel has got again 11 options starting from 1, ending on 12 without 2, and so on. You can continue on that. And for each of the 12 options that Sanchez has, Patel will have 11 different options. So in total, there are 12 into 11, which is basically equal to 132 different options. So here's the working of it. The procedure of assigning offices to these 2 employees consists of assigning an office to Sanchez, which can be done in 12 ways, then assigning an office to Patel, different from the office assigned to Sanchez, which can be done in 11 ways. So by the product rule, there are 12 into 11, which is 132 ways to assign office to these 2 employees. So let's take another example. The chairs of an auditorium are to be labeled with an uppercase English letter followed by a positive integer not exceeding 100. So let's take an auditorium and they are to be labeled with an uppercase English letter. And that uppercase English letter is followed by a positive integer which does not exceed 100. So it's a positive integer, starts from 1 and goes up to 100 but does not exceed it. So what is the largest number of chairs that can be labeled differently? So notice one thing, whenever I'm reading these questions, I'm actually going on line by line and trying to explain each line, trying to understand each line. What does each line say? So the question here is the largest number of chairs that can be labeled differently. So after that, we cannot actually label it. So that's the question here. Or we cannot label it differently. We'll have to use the same alphabets or the same characters. So here's the thing. You've got an uppercase English letter. So in total, how many letters do you have? We can notice that if it's only uppercase English letter, we have got 26 different options. So 26 for the start. And then this is followed by a positive integer that goes up to 100. Starts from 1, goes up to 100. So you have got 100 different options for the second position. First 26 and followed by 100 different options. So for each of the options, you have got 100 different options to choose from for the positive integer. And that means this is a product rule. And since this is a product rule, we need to multiply 26 multiplied by 100. So the answer is 2600. So let's see how the answer is written formally. The procedure of labeling a chair consists of 2 tasks, namely assigning to the seat one of the 26 uppercase English letters and then assigning to it one of the 100 possible integers. The product rule shows that there are 26 into 100, that is 2600 different ways that a chair can be labeled. Therefore, the largest number of chairs that can be labeled differently is 2600. Let's take another example. There are 32 microcomputers in a computer center. Each microcomputer has 24 ports. So for each of the microcomputers, we have got 24 options. How many different ports to a microcomputer in the center are there? I think the answer here is simple. You have 32 microcomputers. For each microcomputer, you have got 24 ports or 24 options. So how many different ports to a microcomputer in the center are there? 32 multiplied by 24 by the product rule. The procedure of choosing a port consists of two tasks, first picking a microcomputer and then picking a port on this microcomputer. Because there are 32 ways to choose the microcomputer and 24 ways to choose the port, no matter which microcomputer has been selected, the product rule shows that there are 32 multiplied by 24, which is equal to 768 different ports. Another example, how many different bit strings of length 7 are there? Okay, so a bit string is basically defined as a string that consists of only bits, zeros or ones. So for each bit, you actually have got two options. You can either have 0 or 1 in its place. So if I use the length 7, so in total, how many bits strings can I come up with? Well, of length 7, the straightforward bit string is 0, 0, 0, all zeros of length 7. And the other extreme is going to be all ones of length 7. And in between, you can have anything that is 1 or 0. So in total, if you want to count the bit strings of length 7, for each option, for each place in there, you've got two options. And since the length is 7, so it is 2 multiplied by 2 multiplied by 2 by the product rule 7 times, which is equal to 2 raised to power 7, which comes out to be, I think, 128 or 5256, 128. Yeah. So it's the answer is 128 probably. So let's see what the answer is. Each of the 7 bits can be chosen in two ways because each bit is either 0 or 1. Bit is basically a binary digit. You need to remember that. Therefore, the product rule shows that there are a total of 2 raised to power 7, which is equal to 128 different bit strings of length 7. And how did I come to it? Because each of the 7 bits has only two possibilities, either 0 or 1. So for the first bit, you have got two possibilities. For the second bit, you have got, for each of the first bit, two possibilities. You have got two possibilities in the second bit. For each of the two possibilities in the first bit, and for each of the two possibilities in the second bit, you have got two possibilities in the third bit, and so on. You can continue on in the same manner. So this is 2 multiplied by 2. You've got 4 options for the first 2 bits. If I take the first 3 bits, I've got 8 options. If I take the first 4 bits, I've got basically 16 options, and so on. So that is how this problem can be solved using product rule directly. Take another example. How many different license plates can be made if each plate consists of or contains a sequence of 3 uppercase letters, English letters, followed by 3 digits. So now you have got 3 uppercase English letters and they're followed by 3 digits. Notice that you can repeat letters. There's no limitation on it. So if the first 3 are uppercase English letters, that means that you have got 26 options for the first place, 26 for the second, and 26 for the third. And this means in total you have got 26 multiplied by excuse me. So in total you have got 26 multiplied by 26 multiplied by 26 for the first 3 uppercase English letters. And these are then followed by 3 digits. So again, you have got 10 options for the 4th position, 10 options for the 5th position, 10 options for the 6th position. So the answer here would be 26 multiplied by 26 multiplied by 26 multiplied by 10 multiplied by 10 multiplied by 10 by the product rule. Because for each of the options, you can repeat the next letter as well. There's no limitation on that. 26, 26, 26, 10, 10, 10. The 26 choices for each of the 3 uppercase English letters and 10 choices for each of the 3 digits. Hence, by the product rule, there are a total of 26 into 26 into 26 into 10 into 10 into 10, which is equal to 17,576,000 possible license plates. Let's take another example, this time from the coding. And by now you are well aware of the for loop and the nested for loop. So what is the value of k after the following code where n1, n2 up to nm are positive integers has been executed? Remember that it's necessary that n1, n2 and so on need to be positive. Otherwise the loop will not run, right? So let's start with k is equal to 0. For I1, which can take value from 1 to n1, we have a nested for loop where I2 can take values from 1 to n2 and so on. The nestedness continues until finally you have got for IM is equal to 1 to nm, k is equal to k plus 1. So for each of these iterations, we will increment k. We start from 0. So the answer here is that for each I1, you're going to run I2 for n2 times. And for each I2, and I1, each value of I2 and I1, we're going to run I3 for 1 to n 3 times, and so on. So they can have different values there. And because of that, the final loop is going to run basically by the product of n1 multiplied by n2 multiplied by n3, so on until nm. So it's a product of all these values. So the initial value of k is 0. Each time the nested loop is traversed, 1 is added to k. By the product rule, it follows that the nested loop is traversed n1 into n2 into up till nm times. Hence, the final value of k is n1 into n2 into up till nm. Remember this, we can again determine this product rule because of the nestedness of the problem. So let's talk about another rule, which is basically the sum rule. The sum rule basically states that if a task can be done either in one of n1 ways or in one of n2 ways, where none of the set of n1 ways is the same as any of the set of n2 ways, then there are n1 plus n2 ways to do the task. So remember, you can either do a task in n1 ways or in n2 ways. So the difference between this and the product rule is that in product rule, for each of the tasks, it had to be done in either of these ways, and then it had to be followed by one of the n2 ways. And because it was followed, and the use of the word that I used there was and, in terms of and, it was a product. When it's either in one of n1 ways or in one of n2 ways, then it's or, n1 plus n2. So whenever there's an or, then, and you need to remember there's nothing shared between n1 and n2. So nothing is common. If there's something common, we need to subtract the common part once only. So in this case, that would be the subtraction rule. But for now, I think the rule here is simple. Whenever there's nothing common between them, and you've got an option to do it in either of n1 ways or in one of n2 ways, then there are n1 plus n2 ways to do the task. Let's see some examples, and that is going to clarify this further. Suppose that either a member of the mathematics faculty or a student who is a mathematics major is chosen as a representative to a university committee. So you're going to choose one representative, and you've got different options. You can either choose a member of the mathematics faculty or a student who is a mathematics major. So how many different choices are there for this representative if there are 37 members of the mathematics faculty and 83 mathematics majors, and no one is both a faculty member and a student? So this is important. So there's nothing common between both the groups of mathematics faculty and mathematics majors. So in this case, it's really simple. You can either choose one of the mathematics faculty. So you've got 37 options here, or you can choose one of the mathematics majors, and you've got 83 options here. So in total, the number of options that you can choose for being a representative to a university committee, the number of options are 37 plus 83, which comes out to be 120. So there are 37 ways to choose a member of the mathematics faculty, and there are 83 ways to choose a student who is a mathematics major. Choosing a member of the mathematics faculty is never the same as choosing a student who is a mathematics major, because no one is both a faculty member and a student. This is important to note. By some rule, it follows that there are 37 plus 83 is equal to 120 possible ways to pick this representative. Let's look at an example. A student can choose a computer project from one of the three lists. The three lists contain 23, 15, and 19 possible projects respectively. So for example, let's say you can choose one project from networks, or he can choose one project from compiler, or he can choose one project from data structures. And if he has an option to do to select one from each of these lists, remember, it's important to know that no project is on more than one list. So each project is exactly one list and is not repeated across lists. So how many different possible projects are there to choose from? The answer is simple: 23 plus 15 plus 19. The student can choose a project by selecting a project from the first list, the second list, or the third list. Again, notice it's or. If it's and, then it had to be a product. So if you had to choose one from the 23, one from the 15, and one from the 19, then there are 23 into 15 into 19 different options. But when you talk about, he has to choose exactly one from either of 23 or from 15 or from 19. So he has to choose only one. In that case, it's 23 plus 15 plus 19, which is equal to 57 ways to choose a project. Let's take another example. And this one, the difference between this example and example 5 that was given previously for the product rule is that The sum rule simply follows that in this particular case, we actually have got n1 options for k for I1 and 2 options for I2 and so on. So for each of these options, it's not a nested loop. So k is incremented, then the next loop runs, and the next loop is basically it's not incrementing things. So in this particular scenario, as you will notice, I1 is 1, 2, and 1. K is k plus 1. So you increment k n1 times. So now the value of k here is already n1. And when you run I2, which takes values from 1 to n2, you run this loop n2 times. You're going to increment n1 plus n2 after that by the end of the loop, and so on until you reach the IM. So in this case, it's going to be a sum of n1 plus n2 until nm. So the initial value of k is 0. This block of code is made up of m different loops. These are not nested loops. Notice the difference. In nested loop, for each of this, you had to run it n2 times. This one is basically a different loop. So each time a loop is traversed, one is added to k. To determine the value of k after this code has been executed, we need to determine how many times we traverse the loop. Note that there are ni ways to traverse the ith loop. Because we only traverse one loop at a time, some rule shows that the final value of k, which is the number of ways to traverse one of the m loops, is n1 plus n2 plus until plus nm. Yeah. So let's talk about some more complex sounding problems where we're going to use both of these or some similar rules. In a version of the computer language BASIC, the name of a variable is a string of 1 or 2 alphanumeric characters where uppercase and lowercase letters are not distinguished. An alpha numeric character is either one of the 26 English letters or one of the 10 digits. So you need to notice that the uppercase and the lowercase letters are not distinguished at all. That is something that you need to know. Moreover, a variable name must begin with a letter and must be different from the 5 strings of 2 characters that are reserved for programming use. So there's a small limitation here that a variable must begin with a letter only and must be different from the 5 strings of 2 characters that are reserved for programming use. How many different variable names are there in this version of BASIC? So the idea is simple. One notices that the name of variable is basically a string of 1 or 2 alphanumeric characters. So if I just talk about it in general, it basically says that it must begin with a letter. So it must begin with an alphabet, and since it should begin with an alphabet, if it's of length 1 only, then you know it has got only one character. So it has got 26 options if it's only 1. But if there are 2, it can either be 1 or 2, which means that this is going to be a sum of length 1 and length 2 alphanumeric characters. If it is length 1, we know that there are only 26 options. If it is of length 2, we can basically, so far what we have read until this point, until variable name must begin with a letter. If we go up till this point, we know that for length 2, it can basically have 26 for the first and 36 for the second. So 26 multiplied by 36 different options for the for the string of length 2. So if I talk about string of length 1 or 2, I've got an option of 26 plus 26 multiplied by 36 as the total number of options that are available to name a variable. But there's one point that we have not addressed yet, and that is that it must be different from the 5 strings of 2 characters that are reserved for programming use. So this is not allowed. We cannot have these 5 different strings of 2 characters. So the answer is simple: 26 plus 26 multiplied by 36 minus 5, because those 5 are not allowed. And these are different number of variable names that are possible in this version of BASIC. So let's see the solution, and then we can move on to the next example. Let V equal be the number of different variable names in this version of BASIC. Let V1 be the number of these that are 1 character long, and V2 be the number of these that are 2 character long. Then by the sum rule, V is equal to V1 plus V2. Note that v1 is equal to 26 because a one character variable name must be a letter. Furthermore, by the product rule, there are 26 to 36 strings of length 2 that begin with a letter and end with an alphanumeric character. However, so 26 letters multiplied by 36 strings of length 2. However, 5 of these are excluded. So v2 is equal to 26 into 36 minus 5, which is 931. Hence, there are v, which is 26 plus 931, which is 957 different names for variables in this version of basic. Let's take another complex example. Each user on a string on a computer system has a password which is 6 to 8 characters long. Okay. 6 to 8 means it can be 6 or 7 or 8, where each character is an uppercase letter or digit. Each password must contain at least one digit. How many possible passwords are there? This is slightly tricky. Let's do the easier part first and let's go for the harder one afterward. First one is there are either 6 characters or 7 characters or 8 characters. So this means you have to, if the password is P, then this is going to be a sum of P6, where P6 is basically the password of length 6, plus P7, password of length 7, plus P8, which is password of length 8. So you have to do all this. Each character is an uppercase letter or digit. This clearly means that, you know, this is going to be 36 characters in total. And in this case, since there is no limit yet, so in total, we have got P6 is basically 36 raised to power 6, because you have got 36 into 6 different options, 36 options for each of the 6 places. So this then comes up to 36 multiplied by 36 multiplied by 36 6 times, 36 to the power 6 plus 36 to the power 7 plus 36 to the power 8. This gives you the final value for P. But there's one thing that has not been addressed, and that is each password must contain at least one digit. So here's a limitation. Each password must contain at least one digit. It can be all digits, but it should contain at least one digit. How many possible passwords are there? Well, the way to counter that, the easiest way is, since you are saying that each password must contain at least one digit, I can read it alternately as all passwords that do not contain any digit are not allowed. Can you think of it like that? So for example, if you've got 6 characters, characters, and each of the characters is an alphabet for sure, then such a password is not allowed, simply. So how many passwords exist that are not allowed? We can just take it out from the number of passwords that are allowed, that we've calculated in total. And from the total number of passwords, if we exclude the ones that are not allowed, we'll be counting the ones that are allowed. And that is the solution here. How many possible passwords are there? So each password that contains no digits will not be allowed. So how many passwords are there? Well, for 6 digits, if you have got all alphabets, this means a possible number of characters that are possible are 26 for each place, and 26 multiplied by 26 multiplied by 26. So in total, you've got 26 raised to the power 6 passwords that are not allowed for length 6. Similarly, 26 to the power 7 passwords that are not allowed for length 7, and 26 raised to the power 8 passwords that are not allowed for different passwords that are not allowed for length 8. So that means that P is now going to be 36 raised to the power 6 multiplied by plus 36 raised to the power 7 plus 36 raised to the power 8 minus 26 raised to the power 6 minus 26 raised to the power 7 minus 26 raised to the power 8 in total. That's the answer. So let's see the answer in writing. How many possible passwords are there? Let P be the total number of possible passwords, and let P6, P7, P8 denote the number of possible passwords of length 6, 7, and 8 respectively. By the sum rule, you have got P is equal to P6 plus P7 plus P8. We'll now find P6, P7, and P8. Finding P6 directly is difficult. To find P6, it is easier to find the number of strings of uppercase letters and digits that are 6 characters long, including those with no digits, and then subtract from this the number of strings with no digits. So by the product rule, the number of strings of 6 characters is 36 to the power 6, and the number of strings with no digits is 26 to the power 6. Hence, P6 is 36 to the power 6 minus 26 to the power 6, which is equal to subtraction of these numbers, and this comes out to be 1,867,866,560 different possible passwords. Similarly, you can calculate P7 as this 36 to the power 7 minus 26 to the power 7, which comes out to be 70 billion 332 million 353,920, and P8 on a similar manner by 36 to the power 8 minus 26 to the power 8, which comes out to be 2,612,282,842,880 different options. So consequently, the P is going to be sum of P6 plus P7 plus P8, which is 2,384,483,063,360 possible values. So notice that if you have so many passwords that you're going to crack, and this is just a password of length 8, how much time does it take? Even if it takes you 1 second to check if a password is correct or not, this is the amount of number of seconds that it is going to take you to crack or check all the possible, enumerate all the possible options. And that's why this password will be really hard to crack. And this is the importance of the counting and then possible application that I've just talked about. Okay, let's talk. This brings us to the next rule, which is the subtraction rule. If a task can be done in either n1 ways or in 2 ways, then the number of ways to do the task is n1 plus n2 minus the number of ways to do the tasks that are common to the 2 different ways. And that's why I told you that the number of common ways, if it is 0, you don't subtract anything, as was shown in the sum rule. But if there's something common, you just subtract the number of tasks that are common to both the different ways. The subtraction rule is also known as the principle of inclusion exclusion. We also call it by the name of inclusion exclusion, the principle of inclusion exclusion, especially when it is used to count the number of elements in the union of 2 sets. So if you remember the formula, in the union of 2 sets, it's the number of events in A1 union A2 is the same as the number of events in A1 plus number of events in A2 minus the number of intersecting events between A1 and A2. So here's the first example. How many bit strings of length 8 either start with the 1 bit or end with the 2 bits 0 0? So here I think the answer is really simple. For the first bit, you've got 1, okay, and the length is 8. So in total, the length of bit strings is going to be 2 into 2 into 2 into 2, 2 raised to the power 8. But since it's going to start with 1, I think the first one is 1. You don't have got 2 options there. So now in total, by just up to this point, you actually have in the first one, you've got 1 option. In the remaining seven characters, you have got 2 different options. So this is going to be 2 raised to the power 7 multiplied by 1, which is 2 raised to the power 7. But then the last 2 bits are also ending with the 2 zeros. So the last 2 bits are also fixed. So this means that you actually have got 2 raised to the power 5 different options. But notice this thing. It's either you start with 1 bit or you end with the 2 bits or both. That is kind of understandably over there. And since it's understandably either you start with 1 bit or you end with the 2 bits, so or possibly both. So you need to take care of this or as well. So if you start with 1 bit, you've got 2 raised to the power 7 options. If you end with the 2 bit 0 0, you've got 2 raised to the power 6 different options. Or if you have got both, there are 2 raised to the power 5 different options. And that means if you start with 1 bit, you've got 2 raised to the power 7, which is equal to 128. If you end with the 2 zeros, you've got 2 raised to the power 6, which is 64. So you've got 128 plus 64 different options. But here's the problem. You need to take out the ones that are basically that have got both 1 bit and all that start with 1 and that end with 2 bits 0 0. So those options are 2 raised to the power 5 different options, which comes out to be 32. So in total, you have got to add 128 plus 64 and subtract 32 from it to get 160 different options. And that is what has been mentioned in this particular slide. Notice that this is done because you have already counted the bits and the bit strings that start with 1 bit and that end with 00 when you are counting either of the first 128 options or the second of 64 options. So you need to take it out once, you don't need to duplicate those options. Okay, let's talk about another subtraction rule, which says that a computer company receives 350 applications from computer graduates for a job planning a line of new web servers. Suppose that 220 of these applicants majored in computer science, 147 majored in business, and 51 majored both in computer science and in business. How many of these applicants majored neither in computer science nor in business? Okay, so the question here is, there are 350 applications in total. Okay, suppose that 220 of these applicants majored in computer science, 147 majored in business. So if I just talk about the number of people who have majored in computer science or in business or both, that is simply going to be 220 plus 147, which is 367 different applicants. But you need to remember that some of these have majored both in computer science and in business. So from this 367 different applicants, you need to subtract 51. 367 minus 51 gives us an option of 316. So 316 applicants were received in total that have either majored in computer science or in business or in both, right? So 316 people have actually applied with this credential. How many of these applicants majored neither in computer science nor in business? That can simply be the number of remaining candidates. 350 minus 316 gives you the answer of 34. So as you can see here in the working, first you need to compute the A1 union A2, which is equal to 220 plus 147 minus 51, which is equal to 316. And finally, 350 applicants minus 316 gives you a total of 34 applicants that majored neither in computer science nor in business. So let's talk about the division rule. There are n by d ways to do a task. If it can be done using a procedure that can be carried out in n ways, and for each way w, exactly d of the n ways correspond to the same way. So each way, if there are n1 ways in total, and for each way w, there are some ways that are common between the different n tasks. In that case, you need to divide this n by d to find the number of ways to do a task. So let's see it by an example. How many different ways are there to seat 4 people around a circular table where 2 seatings are considered the same when each person has the same left neighbor and the same right neighbor? So the answer is quite simple. If you want to consider that 4 people are seated together in the different options, so let's call it person 1, P1, P2, P3, P4, and it's a circular table, so you've got the same neighbors. The thing here is that if you for the moment, let's not think about the circular one, but let's just think about different ways to seat 4 people. And you don't need to, we're not considering the similarity between tables. So let's say that if you've got 4 options, the first person can occupy any of the 4 positions, the second person can occupy any of the remaining 3 positions, the third person can occupy any of the remaining 2 positions, and the 4th position can be occupied by any of the the remaining position will be occupied by the 4th person. So in total, you have got 4 multiplied by 3 multiplied by 2 multiplied by 1 different ways to seat persons. And that comes out to be 4 factorial, which is equal to 24 different ways to order the given 4 people for these seats. Okay, if this is true, we need to consider that we need to exclude, or we need to find out how many seatings are same when the person has the same left or right neighbor. So if the person is sitting on seat 1 and there is the same person that sits on seat 2 and seat 4, this is going to be similar to the position or equal to the position or same as the position where the person is sitting on seat 2 and the same person is sitting on who was sitting on seat 2 is now sitting on seat 3, and the same neighbor who was sitting on seat 4 is now sitting on seat 1. So we notice that there are 4 different options. When the person is sitting on seat 1, that's one possibility of having the same neighbors. When sitting on seat 2, he has the same set of neighbors. Seat 3, he has the same set of neighbors. Seat 4, he may have the same set of neighbors. So there are 4 different options for each person, for each of these settings, where it's the same person. And because this is true for each person, this means that we can simply divide 24 by 4 to basically come up with the number of different seating arrangements of 4 people around the circular table, which are not the same by the rule that has been, or by the limitation that has been given at the top. So in total, you have got 6 different seating arrangements of 4 people around the circular table. And you can count it as well. You can basically put it on a paper and you can count it as we did it in the class. So you can do it as well. Okay, so talking further about another example, and in particular, I will now be talking about a tree diagram. The tree diagram is a very useful tool for counting, and you can actually use this for counting as many things as you want. In particular, for product rule and for subtraction rule, this becomes really interesting and important. So how many bit strings of length 4 do not have 2 consecutive ones? Notice that it becomes really difficult if you want to do it through counting. You'll have to exclude all the ones, all the possibilities where 2 consecutive ones occur. So you need to count them and you need to subtract them from total number of bit strings of length 4. Of course, the total number of bit strings of length 4 is really easy to count. 2 raised to power 4 minus first 2 ones, then second 2 ones, then third 2 ones, and 4 2 ones, followed by 3 ones, followed by 4 ones, etc. So that's the harder part in this. But if you use it, if you draw it through a tree diagram, this becomes much easier, as you will see. The tree diagram in the figure displays all the bit strings of length 4 without 2 consecutive ones. So how a tree diagram is drawn is really simple. You start with the root. You can either have 1 or 0 in the first. So this is allowed. Nothing has been violated yet. If it is a 1, you cannot have another 1 in the second bit. So the only possibility here is to have a 0. So this one is pruned away or cut right here. We don't draw it. We don't move for a 1 here. But in this case, if the first bit is 0, the second bit can be 1 or 0 again. So this is allowed. So we draw both of these. Let's talk about the third bit now. If you had a 1 0, the third bit can now be 1 or 0. Both are allowed. And so you draw it. So if the first bit was 0 and the second bit was 1, then another one is not allowed because that we combine 2 consecutive ones. Instead, only a 0 is allowed and that is drawn. But if it was 0 0, you're allowed to have 1 or 0 both. Similarly, for these third bits, you can possibly have, you can only have 0 here. No 1 is allowed. You can have a 1 or 0 here, a 1 or 0 here, only 0 here, a 1 or 0 here. And that is, you have enumerated all the options. So for example, here we can see that the string here that corresponds to this particular value is 1010. That corresponds to this particular string is 1001, 1000, 0101, 0100, 0000, and that's all the string that have been enumerated. And if you just count these ones that we have reached to the tip, there are 8 bit strings of length 4 that do not contain 2 consecutive ones. And actually, we could have gone the other way and said that, the bit strings of length 4 that are allowed in total are 2 raised to power 4, which is 16, minus the bit string that contain 2 consecutive ones. So 1 1 1 1 1 1 1 0. You can enumerate those 1 1 0 0 1 1 1 0 1 1 0 1, etc. So 4 of those bits and so on. You could move on to the next stage 0 1 1 0 0 1 1 1 and so on. You'll notice that there were 8 of those that contain 2 consecutive ones. You could subtract that and you could come up with the same answer as well. So it's not necessary that we use a tree diagram, but a tree diagram in certain instances is very helpful. In particular, if the number of bits at each step or number of digits possible at each step are limited, like in this case, only 2 were allowed. And if the length of the tree is small, like the depth here is, in this case, is 4, But if it goes to for similar small numbers, it's possible. If it goes till hundreds or thousands, then this becomes almost impossible to count manually. Similarly, if the number of digits or alphabets per place are very small, like in this case, there are two, it's possible. If they are large, for example, alphanumeric 36 or something, then it is also impossible to draw a tree diagram manually. A playoff between two teams consists of at most 5 games. The first team that wins 3 games wins the playoff. In how many different ways can the playoff occur? So in total, you've got this is basically like the best of 5 games. Let's say two teams are playing best of 5 series, and the first team that wins 3 games wins the playoff. So you can stop right there. So in this case, the tree diagram looks something like this. We start at the root. In game one, either team two or team one can win. If game one was won by team two, the game two can be won by team two or team one. And in case the first 2 games were won by team two, the game three can again be won by team two or team one. But if the game three is won by team two, then we can see that we have already got a winner here, and we don't need to compute the rest, and the text can simply be pruned. Similarly, all the ones that are blue here are terminal games, which when a team wins, it wins 3 out of the series, and the rest of the games do not need to be played, and the game has already been decided. So the tree diagram, if you count the number of blues here, it shows that there are 20 different ways for the playoff to occur. Let's talk about another example. Suppose that t-shirts come in 5 different sizes: small, medium, large, and extra, extra large. Further, suppose that each size comes in 4 colors: white, red, green, and black. So for each size, you've got this, except for extra large, which comes only in red, green, and black, and extra, extra large, which comes only in green and black. How many different shirts does a souvenir shop have to stock to have at least one of each available size and color of the t-shirt? Again, if you draw a tree diagram here, the tree diagram in figure displays all possible size and color pairs. So W is for white, R is for red, G is for green, and B is for black, where S is for small, medium, large, and extra, extra large. For small, you've got 4 options. For medium, you've got 4 options. For large, you've got 4 options. For extra large, you've got 3 options. For extra, extra large, you've got 2 options. So count these numbers. In total, you will count the numbers that are in blue nodes here at the bottom, and it shows that the souvenir shop owner actually needs to stock 17 different t-shirts to have at least one of each color and each size that are allowed. So here is a small exercise for you. How many strings of 8 English letters are there that contain no vowels if letters can be repeated, that contain no vowels if letters cannot be repeated, that start with a vowel if letters can be repeated, that start with a vowel if letters cannot be repeated, that contain at least one vowel if letters can be repeated, that contain exactly one vowel if letters can be repeated, that start with X and contain at least one vowel if letters can be repeated, that start and end with X and contain at least one vowel if letters can be repeated. So these are some of the questions that you need to do for practice. And once you are able to do this, I think you are able to solve most of the problems of this particular category in this particular section. And that is something that I'm kind of going to end my lecture on with. In the next lecture, we'll be talking about section 6.2, which is the pigeonhole principle. Hope that you have learned something during this lecture about counting and about the basics of counting. By the end of this lecture, I am hoping that you are aware of, by the end of this particular section, you're aware of some of the basic rules like the sum rule, the product rule, the subtraction rule, and the division rule, and you're able to handle problems that are a mix of these different rules. The main problem I think here is identifying which rule is to be applied. The rules are very simple, but the problem is that you need to understand when and how to apply them. The tree diagram is a very useful diagram that can help in certain instances, but you need to be able to identify when and where to use the tree diagram and when and where to avoid the tree diagram altogether. So that's all about chapter 6, section 6.1. Let us meet again for section 6.2, which is the pigeonhole principle, in the next lecture. Thank you. Take care. Allah Hafiz.